So far, when we've talked about Q-learning algorithms, we mainly focused on algorithms with discrete action spaces. It is actually possible, but somewhat more complicated, to extend Q-learning procedures to the case when we have continuous actions. And that's what I'm going to discuss in the next section of this lecture. So let's talk about Q-learning with continuous actions. What's the problem with continuous actions? Well, the problem is that when you select your actions, you need to perform this argmax. An argmax over discrete actions is pretty straightforward. You simply evaluate the Q value for every possible action and take the best one. But when you have continuous actions, this is, of course, much harder. This comes up in two places: when evaluating the argmax policy and when computing the target value, which requires the max, or, in the case of double Q-learning, also an argmax. So this is the target value max is particularly problematic because that happens in the inner loop of training, so you really want this to be very fast and very efficient. So how can we perform this max when you have continuous actions? Well, we basically have three choices. Option one is to use a continuous optimization procedure, like, for instance, gradient descent. Now, gradient descent by itself can be pretty slow because it requires multiple steps, gradient calculations, and it happens in the inner loop of an outer loop learning procedure, so there are better choices that we could use. And our action space is typically low dimensional, so in some sense it presents a slightly easier optimization problem than the kind of problems we typically take on with SGD. So it turns out that for evaluating the max with optimization, a particularly good choice is to use a derivative-free stochastic optimization procedure. So let's talk about that a little bit. A very simple solution is to simply approximate the max over a continuous action as the max over a discrete set of actions that are sampled randomly. So for instance, you could sample a set of n actions, maybe uniformly at random from the set of valid actions, and then take the Q value with the largest of those actions. Now that's not going to give you an exact max, it'll give you a very approximate max, but if your action space is pretty low dimensional and you can bombard it with enough samples, this max might actually be pretty good. And of course, if overestimation is your problem, this might actually suffer from overestimation less because the max is less effective. This has the advantage of being dead simple. It's very efficient to parallelize because you can essentially use your favorite deep learning framework and just treat these different actions as different points in a mini batch and evaluate all of them in parallel. The problem is that it's not very accurate, especially as the action space dimensionality gets larger. This random sampling method just doesn't actually give you a very accurate max. But maybe we don't care about that. Maybe if overestimation is our issue, maybe a worse max is actually all right. If you do want a more accurate solution, there are better algorithms that are based on basically the same principle. So cross-entropy method is a simple iterative stochastic optimization scheme, which we'll discuss a lot more when we talk about model-based RL later, but intuitively cross-entropy method simply consists of sampling sets of actions, just like in the simple solution above, but then instead of simply taking the best one, cross-entropy method refines the distribution from which you sample to then sample more samples in the good regions and then repeat. And this can also be a very, very fast algorithm if you're willing to parallelize and you have a low dimensional action space. CMAES, you can kind of think of it as a much fancier version of CEM. So it's substantially less simple, but structurally very similar. And these kinds of methods work okay for up to about 40-dimensional action spaces. So if you use one of these solutions, you simply plug this in place of your argmax to find the best action, and the rest of your Q-learning procedure stays basically the same. Another option that you could use, option 2, is to use a function class that is inherently easy to optimize. So arbitrary neural networks are not easy to optimize with respect to one of their inputs, but other function classes have closed-form solutions for their optima. One example of such a function class is the quadratic function. So you could, for example, express your Q function as a function that is quadratic in the action. And the optimum for quadratic has a closed-form solution. So one of the ways you could do this is something called the NAF architecture, proposed in this paper by Shishiangu in 2016. is to have a neural network that outputs three quantities: a scalar valued bias, a vector value, and a matrix value. And the vector and matrix together define a quadratic function in the action. So this function is completely nonlinear in the state. It can represent any function of the state, but for a given state, the shape of the Q value in terms of the action is always quadratic. And when it's always quadratic, then you can always find the maximum. In this case, the maximum is just mu phi of s, as long as p phi of s is positive definite. So this is called the normalized advantage function. And the reason that it's called normalized is that if you exponentiate it, then you get a normalized probability distribution. So the argmax of q phi is mu phi, and the max is v phi. So now we've just made this maximization operation very easy at the cost of reducing the representational capacity of our q function. Because if the true q function is not quadratic in the action, then of course the problem we have is that we can't represent it exactly. So there's no change to the algorithm. It's just as efficient as Q-learning, but it loses some representational power. All right, the last option I'm going to discuss is to perform Q-learning with continuous actions by learning an approximate maximizer. This is going to be a little bit similar to option 1, only instead of running the optimization separately for every single argmax that we have to take, we'll actually train a second neural network to perform the maximization. So the particular algorithm that I'll describe is most closely related to DDPG by Lillicrap et al. in iClear 2016, but DDPG itself is almost identical to another algorithm called NFQCA, which was proposed much earlier. So you could equivalently think of this as basically NFQCA. This algorithm can also be interpreted as a kind of deterministic actor-critic method, but I think it's actually simplest to think of it conceptually as a Q-learning algorithm. So remember that our max over A of Q phi SA is just Q phi evaluated at the argmax. So as long as we can do that argmax, we can perform Q-learning. So the idea is to train another network, mu theta s, such that mu theta s is approximately the argmax of Q phi. And you can also think of mu theta s as a kind of policy because it looks at a state and outputs the action, specifically the argmax action. How do we do this? Well, you just solve for theta to find the theta that maximizes q phi at s comma mu theta s. So you basically push gradients through your q function and maximize. And you can use the chain rule to evaluate this derivative. So dq phi d theta is just dA d theta, which is the derivative of mu theta, times dq phi dA. So you can obtain this derivative by backpropagating through the q function and into the mu, and then into the mu parameters. So now our targets are going to be given by as yj equals rj plus gamma times q phi prime evaluated at sj prime comma mu theta sj prime, which is really an approximation for the argmax as long as mu theta is a good estimate of the argmax. So here's what that algorithm would look like. Step 1, take some action AI, observe the corresponding transition Si AI Si prime Ri, and add it to your buffer, just like in Q-learning. Step 2, sample a mini batch Sj Aj Sj prime Rj from your buffer uniformly at random. Step 3, compute your target value, and now instead of using the argmax, you're going to use mu theta. And in fact, you're going to use mu theta prime. So you actually have a target network for q phi prime and a target network for mu theta prime. And then step 4, just like in Q-learning, perform a gradient update on phi. And additionally, we'll now perform a gradient update on theta. So the gradient on theta uses that chain rule derivation for the gradient that I showed in the previous slide. So it takes the derivative of the q value with respect to the action, and then multiplies that by the derivative of the action with respect to theta, which is just backpropagation through mu. Then we're going to update our target parameters, phi prime and theta prime, for example, using Polyak averaging. And then we'll repeat this process. So this is the basic pseudocode for a continuous action Q-learning algorithm. In this case, this particular algorithm is DDPG, but there are many more recent variants as well as older variants. So for classic work on this, you could check out an algorithm called NFQCA, For more recent variants, you can check out TD3 and SAC.